Okay, let's start with the 1D heat equations, and let's drive the 1D heat equation from a physical phenomenon. Then we will try to drive that phenomenon to our PDE, the mathematical form, and then we will set up the conditions, either initial condition, boundary conditions, to solve the PDE. Okay, so let's start with the example 1D heat equation. And we will try to use 3 steps to learn about this 1D heat equation, the PDE. So to learn PDEs, the first is deriving mathematical form of the PDE from physical phenomenon. So deriving PDE from physical phenomenon we here particularly showing is the heat transform. Okay. Then the second is we will solve the ODE, solve the PDE using either initial conditions, boundary conditions, or a mix. Okay. Then the third step is we will try to explain what is our result look like to build on the physical explanation. So interpretation, building physical explanation. And let's start with the simple example. Let's start with this 1D heat equation. Okay, so let's consider an example. Consider the temperature distribution which is U. So this is temperature function as function of space and time in a thin metal rod. And this is a 1D model, okay, 1D model. So you have a thin rod and you have some function of the temperature as function of space and time. So this is x direction, which is the space, 1D space, is from 0 to L for this rod. So the length of the rod is L. You have function of temperature as function of x and t. T stands for time. And when we derive some physical phenomena to mathematics, usually the first thing we will think about is some conservation law. For example, it can be energy conservation, it can be momentum conservation, it can be mass conservation, or you can also have laws from first thermodynamic law versus second thermodynamic law. So we will think about those laws to derive our physics to mathematics. Then for this heat transfer, we will talk about the energy conservation. So conservation of energy. This system, what we are interested. So we have to think about our goal first, then build the conservation of energy to achieve our goal in the end. So the interest goal, what we are interested in, we want to know what is this UXT, right? So we want to know the solution of this UXT. That means we want to get the temperature or the temperature change as function of x and t. So the rate of temperature, which you can represent the temperature is uxt here, in time and space. So that is what is our interest. And based on this interest, we will use the conservation of the energy to derive some mathematical form from the physical phenomenon. So we can write in text first, then code it in mathematics. So the word we are interested in is the rate of change. Instead of temperature, we think about conservation of energy, then that will be the rate of change of heat energy. What the rate of change of heat energy equals to? It will equals to the heat flux. So heat flux through the boundary and the boundary can be at some x at some point. N plus some heat source. This heat source, you can think about many heat source, or it can be some temperature, it can be some energies, it can be even chemical kinetics, which these chemical reactions will generate heat, or it will consume some heat energy. So that heat source can be anything. It can be from magnetic heating, etc. So that is the heat sources, or you can also say heat generation. Either this generation is from reactions, chemical reactions, or it can be electromagnetic driven heat generation. So the rate of change of heat energy will equals to heat flux through the boundary at some point x plus the heat source or heat generation. Well, if we code it into mathematic form, what we have, what is the heat energy? What is the heat energy? So the heat energy is Cp rho. This Cp can be as function of x. The density can be as function of x uxt, which is the temperature. So this is the specific heat capacity. This rho is the density, and this uxt is the temperature as function of space and time. Okay, and this is the rate of change of the heat energy, so it should be d over dt. So the change of this heat energy as function of the time, and that will be equals to the heat flux, which is minus dq over dx, plus the big Q is represents the heat sources, which is qxt. So this is the heat flux term. Okay. Then we code it in mathematical form of the interested goal, the rate of the temperature change in time and space. Okay, and we are using the conservation of the energy. The next part we will talk about the heat flux term and how we can drive this PDE into a 1D heat equations we talked about before.